Welcome to VALU's First Training Session Part 2. This session will cover 6 more verification and validation methods and tools that are going to be addressed during the project. It is now time to start the session. Enjoy.
I'm Thomas Bauer. I'm with the Fraunhofer Institute for Experimental Software Engineering in Kaiserslautern, Germany. And today I will talk about our virtual validation method, which is called Virtual Architecture Development and Simulated Evaluation of Software Concepts with the tool framework VAL. So this is joint work with my colleagues Adam and Donald. So today I will basically give some insights of the method and also of the tool, also with some concrete examples. So basically, when we look at the development process of today's complex systems, we usually need a systematic process model for that. So everybody's aware of that with dedicated specification design techniques, top-down approach. We have the integration and the testing activities, which are basically conducted in a bottom-up way. And usually these things are quite expensive here due to the, let's see, late test stages and the late possibilities for detecting the critical issues in complex systems. Yeah, and usually nowadays many systems are developed by integrating existing parts. So let's see, the main innovations, the majority of the new features is realized by the system integration. So basically this integration part and the higher level activities in these processes, they become more important here. In the basically in the technical systems, we see then, or we have a tight connection of the actual test objects and the environment. So we need then dedicated facilities for that here, especially then to for checking software models and the hardware. So we have the hardware loop simulation. Basically, then it's the integration of a control unit with its environment, and so we have further techniques here. So what we basically aim at is to validate things, validate properties as early as possible in the process. Yeah? So this is then realized by so-called shift left, and basically by using different kinds of models and different kinds of validation approaches. So basically here then the possibility of already checking software, checking models early, also in connection with the environment, so then basically in the loop. Yeah. So basically for today's systems and the challenges, we have to consider additional paths. So just, let's say, using models as some representatives of a system and then applying them for studying properties by analysis or verification is not enough. If we really aim at this new complex system, really this digital ecosystems, smart ecosystems, we have to go one step further here in order to really make sure that the new concepts, the new features, the new innovations are feasible with the current setup. So that's why additional stages are added here. We call it here those requirements loop simulations, basically at the early stages of development process, when you basically define your requirements, you define the drivers for the architectural decisions. You have to validate already if this is feasible. You have taken certain decisions already, and you have to check if it's really feasible, and you need infrastructure for that. Yeah. For the other phases here, basically for, let's see, testing on the model level, software component level, and later on also for the hardware, dedicated infrastructure and tooling is available. But for the aspect of integrating different systems from different domains, from different classes, yeah, so heterogeneous systems, this is really a new topic. Yeah. So basically what we did at the Institute was to develop a dedicated tool framework that explicitly addresses this stage and the challenges of the early validation and the coupling of different systems and different executable artifacts. in order to enable an early virtual validation, really with pure virtual setup, virtual components, virtual environment. So that's our approach here and the corresponding tool VAL. The features in a nutshell. So VAL stands for the framework for the evaluation on requirements and architectural level. So you see here really we are focusing at the earlier stages here. It's about modeling and design, but it's not another modeling tool for specific aspects. It's really that we support different kinds of simulation models, yeah, with respect to the degree of abstraction, the behavior types, and also the degree of details here. And another thing is that we are able to couple different tools. We are a platform for coupling tools, for coupling simulators, also for enabling co-simulation. Yeah, so there are also the different means here. For example, by a generic network connection via UDP or TCP or via shared memory, also tool-specific connectors. So these are available. Currently also there are a set of tool connections already implemented, for example, for Simulink or System C. So basically here then we are enabling a focused validation on specific abstraction, on a specific abstraction level here especially the validation on the based on high-level requirements and architectural concepts. Yeah. And so we are able to provide prototypes that can be used for the verification. Yeah, executable prototypes that we really need to assess properties that really needs execution, that needs to be tested, that cannot be analyzed. Yeah, the analysis of requirements is still there, but you can really get confidence on your concept, on the new features, if you have an executable environment you can really use and for the validation. You can use it then also for dedicated X-loop activities here, especially on the higher levels, basically requirements, system architecture level. Yeah, for the simulation, for the simulator coupling and the connector here, we are able then also to flexibly connect different tools here. That's really the advantage, really flexible tools. You do not have to rewrite the models, change everything. Really existing work, existing tools, existing expertise can be integrated here, yeah, to really assess your system design concepts, explore the design space, and really enable a more holistic evaluation at an earlier level. Yeah. So basically, that's the VAL features in a nutshell here, so that we're really able to enable a reliable validation of the complex systems by integrating different heterogeneous components, also enabling a holistic testing with respect to specific goals, yeah, in a fully virtual environment. Yeah, so that's basically the VAL nutshell. Here's some USPs. I will maybe highlight the relevant ones here. For example, if you want to connect black box models here, yeah, due to, for example, IP protection. Yeah, so basically you are an OEM, you're an integrator, you would like to check already executable artifacts from your suppliers. So then the question is how to integrate black box models. Yeah, in many cases you really need them locally, or you need to have you need to access them. So here we are able with our infrastructure to also to connect remotely to black box simulation models and also other tools. Yeah. Or for example, if you want to check specific non-functional requirements early, then you can do this by adding, of course, the dedicated models. If you're interested in performance, you need to have a model that provides the performance properties. But here, with the VAL framework, you are able to execute them and validate them. Yeah. Or for example, if you want to set up a simulation scenario fast, yeah. So here you get the means by connecting different components together with dedicated communication middleware. Yeah. Or also you can just add another conceptual behavior model here, because it's a component that is still not exist. You can add them a behavior model here of different notations and just connect it to the other parts in order to really run the validation. So that really advantages here that facilitate an earlier validation of the system. So these are the main benefits. So in order to support that, we have created a library also of simulation components where we basically cover different aspects here, for example, different semantic models. So basically also you can then integrate components which are event triggered or which are time triggered, discrete time, continuous time. You can use directly dedicated behavior models. You can connect to a specific to executables in different languages, for example, Java or C++. You can use existing components of let's see, standardized interfaces here, like the FMUs. You can connect the systems with dedicated network models. Here basically we are supporting general network models, but also automotive specific network models, for example, the CAN, the FlexRay, LIN and MOS, but also generic ones like Bluetooth or let's see, wireless connection here or Ethernet connections. In the project now in values, we are extending that also for dedicated communication protocols for industrial automation, for example, OPC-UA and MQTT. We are currently working on that in the use case 4 together with Pumacy. We also support dedicated host platforms with single core, multi-core, with different operating systems. If you really want to assess the impact of a certain decision with respect to host platform, the deployment of your applications, on the overall system performance, on the basically quality of your concept. So that's also possible. So here we are able to validate your decisions at different levels. So you can really see we also go down basically to the really execution platforms, to processor platforms, to operating system. That's also, if it's needed, that's possible here if a certain decision has to be taken. And on the other side, there are also means for really connecting conceptual components or existing prototypes or existing codes together to really assess a new concept, to really assess a new feature here. So with respect to the reference architecture, so when we use the FARAL for our virtual continuous integration activities here, so basically what we have is we have the possibility of basically managing and running components in different domains, also to enable nested domains, to really connect components from different domains. For example, a component that runs in a time-triggered domain, so a time-triggered component is connected with a event-triggered component, or component that really runs in real time. So here basically there is the challenge to really synchronize and couple the different behaviors so that you get really then a deterministic behavior out of that. So that's the question, okay, how to schedule the components, how to enable the data flow within the system composition here. That's a tool question. It has been solved. So really you can use it then for your validation. And also the question is, okay, how to connect then the different tools. So there, as I said, available connectors here for different environments here, so for different tools, different simulation environments. Also, there's the possibility of logging and evaluating system properties. So this means basically you have to assess the data flow in the system, compare it then with your expectation in order to identify issues and in order to identify violations and failures here. So that's possible by monitoring and logging library here, and also there's a possibility of visualizing aspects here. Because the tool framework is really flexible. So it should be really we wanted to be able to connect to different environments or to enable the different user groups to connect the tool framework to their tool chain here. So then also the visualization is important. For example, you've used Unity also for visualizing specific data here, but it depends on the use case. So it's really flexible here, and we covered and solved many questions that come up at this early validation, really when you connect different parts together. Yeah, when the single, basically the single tool questions or the single simulation models are well covered, yeah, with dedicated tools, with dedicated approaches, but the integration level, the interaction, when you want to connect the things, when you want to combine the things, this really needs a technical infrastructure, sophisticated one, and then VAL is a solution, our solution for that. Yeah. So as I said, we are able to address different levels here. Yeah, for example, also the functional level, that we really come with a model, a distributed composition of simulation models in order to check especially functional behavior. Yeah, does this new feature, or is the new feature feasible? Yeah? Does it really fit? Does it meet the customer expectations? But if you're interested in more detailed and other quality characteristics, for example, scheduling issues here, or fault injection to hardware, or the performance of your low-level architecture, or let's see, the question with respect to power consumption, then you need other models here, and we are able to integrate these models. Yeah, for example, the System C, Gem5, and so on. Yeah. That's on the hardware level. Also on the interaction level, we have also connected the VAL tool suite to typical tools like the CANOE or the NS3 simulator here. Now I will talk about some case studies here, because it's always interesting. Okay, how this was applied. Yeah, this was basically now the theory and the general introduction, but how it was applied. So basically, where we came from, our first users of this technology came from the automotive industry here. So here, basically, the requirement was to integrate different tools and different platforms via unified API. Yeah. In this case here, the customer wanted to connect, yeah, basically different virtual control units, want to connect the control units that have been specified in Simulink. There were System C components, Almatea, functional mockup units, and they should be connected in order to enable specific validation. So basically, they are connected via dedicated communication buses. So in the automotive framework, it's then CAN FlexArray, also LIN-based networks. So we supported that, and that's part of the library here. Yeah. So then, usually in the project, we developed the connectors here, enabled also the connection via the distributed components and UDP TCP or shared memory, and the simulation system is compatible also with different Windows and Linux distributions here. This was also a requirement because the customer works on different sites, also with different hardware setups. So the simulation should be also supported and should be also executed with different operating systems and platforms here. And here we implement then dedicated functions for the control of the simulation, for the connection, the management of synchronization, role frame coding, and so on. Yeah, so it was really then enabling the customer to simulate complex networks in the automotive domain with several components connected via different buses here in order to develop really new features for the next generation of vehicles. So here's one example here, basically one data flow where different components were exchanging then the data, just to show you how the tool works, visualization here, and basically components were then connected via the UDP, and VAL really worked then as the server, and the master component here, which basically synchronized then the traffic flow and connected in different components here. Yeah. So this was one use case that we had directly from the industry, and basically when we do things, then it's then it should have always direct industry impact. So I think that's why it also fits quite well here in the values project, because we develop things that have been already used and proven in real industrial projects here. That's important for us. In the values projects, we are working on dedicated extensions. Yeah. So the setup was then the following here for this project, that then the Feral framework here has been set up. The dedicated bridges and connectors have been created, and we were able then to run the scenarios with these different components and the connection of different tools, basically system C components interacting with a component that have been designed in MATLAB Simulink. FMUs have been used. And so this was then basically the setup here. The connection was realized then via different virtual communication buses, as I said, like the CAN, FlexRay, and so on. And the customer was then able to design and also validate these new functions. Yeah. So that's a quite nice result here. So then also for the specification of the simulation scenarios, so there are different means. I said we want to be quite flexible in our basically in our tool suite. So basically customers of different groups here, also with different expertise levels, should be able to also define the simulation scenarios. Yeah. And here's one mean of that. So we have dedicated, we call it property files here, where we then define the elements of a simulation scenario. Basically, yeah, what are basically the actors of that? What are their properties? What is the interface? How the interface is connected? What is the general setup of the simulation? Yeah, for example, the duration of the simulation, step time. What is basically the modeling domain of that? Okay, it's time domain, event domain, is it real time domain? So we are able then to specify the simulation scenario, and basically the generation of the artifact and the deployment of the different artifacts, connection of the artifacts, deployment to the host nodes, that's then automatically done by the tool suite. Yeah, but we have to specify it, but the rest is then done automatically. Yeah. So there are some manual steps, but also several automated steps already. So, and here we just see an example here for the connection to Simulink. So basically in the Simulink model, we have then also dedicated blocks for the Feral communication, basically then input and output blocks that serves for then the connection with the Feral component, which is then basically, which serves then for the transmission of the data to the other components and the basically coupling of the whole tool infrastructure here. So that's the outcome here, just that when we run the scenarios, so that's already working. So here we see then basically this functionality discretizes then a certain data flow. Here is just a connection that was shown here. So we are really able also to run these scenarios and also then to evaluate it. Yeah. That's then another point here is our demonstration project here. So we have an internal demonstrator for just trying and developing new features here. It's our advanced driving function Validator, which is basically it's a racing game platform here, the Anki Overdrive that we've used for the validation of certain concepts here. And here we wanted to use Feral, want to also show the applicability for checking specific driving functions, so advanced driving functions, for example, obstacle detection, automated overtaking, platooning, adaptive cruise control. And we want to connect also then different technical entities here. Here, for example, cameras have been connected. We also can connect it, the simulation environment with the real devices, with the Anki cars. Basically, it's a Bluetooth connection then. And for us, it's basically then a demonstrator for just trying new concepts and showing them. Yeah, there was a connection to Unity for visualizing that. And so this was a quite nice platform because we have also the direct feedback from the hardware here. Yeah? So we control the cars and we get then basically responses, then the speed and certain other parameters. It's simplified, but I think it's a nice demonstration platform here. So the setup was the following here. We have used another tool for the specification of these scenarios, Blockly. I will come to that later. We use the Anki Overdrive already for reading the car data and really controlling the car. So we send control commands and reading specific car characteristics here. So we connected then cameras also just to check where the cars are, just to have another data point for the position of the car, which was then more accurate than the ones that we got from the Anki platform. And we had a visualization of the Unity framework here. Yeah. So in that project, we also then developed also dedicated language for specifying the scenarios here. So that's much more detailed than the one that I showed before with this property. So it's really here you can define your basically the components of the simulation. You can define also interfaces, connections. That's very detailed. So you have really full control of that. And for basically for the engineers that really want to have full control of all components, that's then the choice, basically the domain-specific language for the simulation scenario here of that platform. Yeah, so you were able then to connect components, parameterize components, import and exchange connectors here, replace also components. That was then easily possible with that. That's a point. And another point is the specification of the simulation scenario done by Blockly. So some of you might know that it's a graphical programming language, and we use that in order to enable also non-expert users to create a simulation scenario. So basically here they were able to really define a scenario of that racing car. So basically the idea is, okay, if there's an overtaking function with cruise control, how can I basically, it's about configuration, right? About the configuration of the speed, configuration of the behavior, defining thresholds, defining what if conditions, what happens if I reach a certain threshold, if I enter certain safety critical distance, or safety distance here, what should happen, should I change the lane? And here in Blockly, with really simple means, also non-expert users are able to specify these scenarios, which are directly transformed then to a script that is executed then in the Ferrari platform. So that's also a very good result here, that also users with different background and different expertises are enabled to validate things. Yeah, depending on your expertise, depending also on your goals, you can do it at a very low level, very specific, or at a very high level. But you will be then enabled to automatically validate it. Yeah. So basically, here, so for example, here in the red block, the ACC behavior is specified here with respect to speed and the safety distance. So the units are basically here in the millimeters, a millimeter per second. So it's different because our world basically is defined like that. That basically distances are measured in millimeters, and also speed is then measured in millimeters per second and not in meters per second. Yeah, to also use then integer values here. So there's another part with respect to the car detection avoidance. So basically, that's another threshold tier that usually covers this overtake. Yeah. The question is then, when should the car follow the leading car, or when should I overtake? And then I can configure that. Yeah. And here we see then one scenario. Basically, two cars are configured here, the blue one and the red one, with different basically values here with respect to the speed. Yeah, and so let's look at this figure here, how this really works. So in one scenario here, so we have a dedicated safety distance and a dedicated basically distance for the overtaking. And here the ACC safety distance is 800 millimeters. The CDA safety distance, so basically for overtaking, is shorter. So basically when you basically approach the leading car here, then the ACC safety distance is entered first. Yeah, so basically, and you would follow that. Yeah, so ACC is triggered first, so we follow that. If we configure it in a different way, basically that the overtaking distance, yeah, to avoid a collision here, the CDT safety distance is greater, then basically would expecting different behavior. Yeah, here CDT safety distance reached already at 800 millimeters. So then the car would overtake because the one has then the higher speed, 800 millimeters per second. The car would then overtake, and I would not enter this ACC controlling mode here. Yeah, so I can really try out different configurations of the system. Yeah, play really with the numbers and assess my design and configuration alternatives. Yeah, this was what we wanted to do here. There were several other scenarios also with traffic on the other lanes. What happens then with the traffic? Also with the basically the number of cars, the frequency, and so on. So different really scenarios could be considered. So we were able then also to use then Ferrari in this context, connected to real components here, yeah, with the real sensors and real actuators, even if it were a racing game. But we are also able to connect them, and that for us it was an important also demonstrator showcase to really to show that. Yeah. Yeah. So we applied it in several demonstrators here. In the values project, we are working on the industrial automation use cases here, especially use case for with Pumacy, where we do not deal with cars, but with robots, robot models, and also sensors of these robots. So then it's a question of how basically the data flow can be represented, how the dedicated communication networks are presented here. And so it's basically a different setup, but the challenge is sound like similar. We want to early validate new concepts here with dedicated tools, dedicated environments, and we want to able to connect it and to validate it and to assess specific characteristics. Yeah. So basically then it's a question of, okay, are there additional tools, additional communication networks that have to be supported, but the general setup, the general idea is the same. Yeah. So just to summarize then the talk here, basically at the beginning we talked about the need for the shift left and the virtual validation. So here we really want to enable the customers to early validate their concepts, their requirements, their new features. Now we will do that with our Ferrari system here, which is a flexible framework for connecting components, for coupling different tools. We have a set of components in our library that are already available here, also for the projects with different kinds of component models, different kind of network models, different kind also of fault injection models here. And we have also different means for specifying a scenario. Yeah, textual means, also then the graphical languages here with the Blockly. So the different means depending on the user group. And here in the values, basically we're extending it also with respect to the automation, with respect to the component types, network types that are needed also for different domains. Yeah. Thank you.
So welcome everyone. In this presentation, we look into using simulators for testing and training machine learning based system like autonomous driving system. We introduced CARLA, an open source simulator that generates realistic simulated sensor data like camera images, radar point cloud, GPS coordinates, and other kind of sensor data. And we further introduce OpenDrive and Open Scenario standards that cover other aspects of a realistic simulation. And finally, we demonstrate how an area within Gothenburg, where we are working, can be modeled in this simulator. So I think I can skip this slide because everyone here know about Values project. And to start my presentation, let me show you some video clips from Boston Dynamics company and how inhumane these smart systems are tested. Sadly, it's not only American Boston Dynamics that uses physical environment to test their system. And this is a practice that is even common in Europe. So Euro NCAP is a series of vehicle tests that represents, in a simplified way, important real-life accident scenarios that could result in car occupant or other road user being killed or injured. Apart from this method to be very cruel, running a ML model in a real world is very common. It's very common to run an ML model in real world to train them and giving the model the chance to live in the real environment and learn how to survive and get better and improve itself by interacting with the surrounding and by the environment, I mean. But the real challenge for automotive industry is that it's not a good idea to let a naive autonomous car driving around in a city and crashing into people, hoping that it is eventually going to learn how to drive, you know. As a result, we usually end up with these test tracks that I showed in the previous slide, with some humanoid like robots or humanoid models, like to test very simplified scenarios. But even these test tracks are not solving all the problems that we have. The first issue is the coverage of scenarios. These test cases are very specific and they cover only very basic scenarios and situations. Well, as you see in the documentation, these tests are very specific, that they even mention the color of the trouser and the shirt, and they should be like the color, and like they're very specific. They are not very generic. And the second issue is safety. Like even though we are using this humanoid, but in many cases we are using the real driver to crash into this humanoid. And as you can guess, it can still be very dangerous. And finally, it's very costly because like you have to set up this stage, drive into them, measure stuff, and then go back and repeat these tests many times and many times. Apart from being very costly, the car or the ML model behind the car should consistently make the right decision. Not only once, but also maybe thousands or millions of times. So like any minor change in the ML model might probably means that we should test the entire system again. And yes, sometimes we have the money, but we don't have the time to perform these tests. There are other, like as you say, this is a scalability problem, and sometimes it's very hard to reproduce some of the tests. So simulation seems to be an ideal solution, both for training and for testing. You can train your model by leaving it alone in a simulator and letting it learn by interacting with other actors. By actors, I mean cars and objects and buildings. And later test your model in other environments or in some specific corner case and see how it learned from from the previous environment. This is easier said than done. To achieve this, you have to simulate the environment, sensors, and the actuators in a very realistic way. But once we simulated the sensing and the actuator, input and output, you can test inner components of your system, like the perception component, the planning component, or the decision-making component. So you implement the simulator once, and then you can test it to test different components. Before I continue, there's a disclaimer here. Simulators are amazing for testing and training ML systems, but they are not the final solution. Simulators have some shortcomings, like they only simulate one or a few aspects of the real world or the real system, and they are not usually as realistic as you want. But my take on this is that even though they cannot entirely replace the test track for testing in a real environment, but they will gradually take over most of the responsibilities. Another point is that if your ML model is not working on simulator, you can forget about trying it in a real world. So this is the basic requirement for even considering a ML model for real usage. And this early decision can reduce a huge amount of cost. You can easily filter out a lot of ML models that people claim to work perfectly fine before you trying it in a real world and the real world, real hardware, real situation. So there are other items, or there are other points that we can test our simulator, like training our model on a simulator and testing it on a real world, which is it's very hard to reason about it. The same with training it on a real data and testing it on a simulator. These are very tricky corner cases that it may seem reasonable, but it's very hard to reason about it. And they are still under research. But it's something that we have to have in mind for future. So I promised that I'm going to introduce a simulator for this presentation. The simulator that we discussed in this presentation is called CARLA. CARLA's goal is to mimic driving in the real world and has been developed from ground up to support development, training, and validation of autonomous driving systems. In addition to being open source and having open protocols, CARLA provides access to open digital asset library, which contains layouts, building vehicles that are created for this specific purpose. And you can use them freely for your use. And big names are behind this simulator, like University of Barcelona, Intel, and Toyota. For testing an ML model in a simulator like CARLA, our first goal is to make everything as realistic as possible, just to test the happy cases. Can the car drive in a normal situation? And once we are sure that normal happy cases are like we can drive or the system can work in a normal situation, we can tweak the reality to see how the system behaves in coordinate cases. So the first step is to have a realistic simulator before starting injecting faults and considering corner cases. And in the coming slide, I will explain what I mean by a realistic simulator. As you see here, you see that's like in a realistic simulator, like when there is a wind, the trees are shaking, when like the light here affects the shadows, and yeah, when it's raining, there might be reflection of water on asphalt, basically. And yeah, you can see shadows again, and also like things on like asphalt that can changes the visual of a road, basically. And many items that can appear beside the road. Just look at the details and like try to understand what I mean by a realistic simulation. So when I say realistic, I mean realistic from 4 aspects. And like 4 aspects are considered in CARLA. Realistic graphics, realistic physics, realistic sensors, and realistic actuators. And I will explain which part of CARLA is responsible for each. CARLA support realistic graphic and physics by using a very famous game engine called Unreal Engine. If you're into gaming, you definitely have heard about this engine. So the game engine takes care of materials, lighting and shadow, texture, color, distortion, and so on. And there is also like Unreal Engine is not only a graphic engine, but it's also a physics engine that takes care of like physical behavior, like collision, gravity, friction, and so on. These are all done inside Unreal Engine, like CARLA. CARLA basically specify them, and Unreal Engine take care of them. But there are also realistic sensors like radar, LiDAR, GPS, and like realistic cameras, basically different kinds of camera, like depth map or segmented images that you can specify what each part of image is. You know, is it a vehicle? Is it a building? Is it a road? That's called segmented images. And this RSS is a safety sensor, which tells you how well the car is driving within the road. Yeah, basically, it gives the car a point how well it's driving. Yeah, and CARLA also has a realistic actuator like steering wheels, gas and brake pedal, and yeah, realistic moves. I will show this in the demo later. So we talk a lot about realistic environments, but we thought, why not picking up a realistic area with all traffic complexities, with like, I mean, pedestrian path, intersection, traffic lights, bicycle path, tram line, buildings, trees, so on, and see how can we model it inside CARLA. Now that we know what we mean by realistic simulation, let's take a look at the different components. Like, remember this location. I will later show how this area is simulated in the simulator. Yeah, we will, in the next slide, we'll also see how these components, such as road network, traffic scenarios, and different sensors like cameras are specified in the simulator. So, so we want to have a realistic traffic network, and there is a standard called OpenDrive standard, which is integrated into CARLA, which describes the static road elements, such as the how the road look like, basically. And if you just and it uses some very basic geometric shape to describe complex roads. And it's, if you open up an OpenDrive file, you see an XML file. And without going into detail, you can see that this OpenDrive file describe things based on a simple geometric shape like spiral and lines and things like that. So like you can describe a road by composing these geometric shapes. Now that we described the road, we can describe the driving behaviors of actors. For example, you can describe how cars are maneuvering within the road. And basically, OpenScenario has a sort of event-driven programming in which different event triggers actions. For example, you can write something like at time t, go from point A to point B using path P. You know, it has a language like that. Or you can which helps you easily describe a situation like this. When you get close to the blue car, increase your speed to 10 or press the brake pedal. Like it has a language like that. And this is an example of an OpenScenario file. Again, you can describe the vehicle and its dimension and when things should happen, basically. I talk about realistic camera, which means that CARLA lets you define the size of images, different property like horizontal field of view, ISO, and different things that I'm not knowledgeable enough to explain them, basically. And it also supports like distortion attributes. Like old cameras, if you remember, they were like somehow black in the corners. There was some blackness in the corner. You can describe them. You can like set some parameter and make these kind of filters possible, or this type of distortion possible. And again, a simulation is like something that you should also consider, that when you take a picture of a moving object, it's different from taking a picture of an object that is not moving, which is called like motion blur. You can easily change this parameter to make your simulation even more realistic. So these are just attributes that belong to the camera. And there are tons of sensors, not tons of, there are several sensors that each of them have their own parameters. Before I go into the demo, let me emphasize that in this demo, actors are either controlled manually or run by autopilot, which means they are acting autonomously. Basically, what I'm trying to say is that there is no ML algorithm behind the scene. There is a God agent that knows everything and control all the actors, and decide where each car or agent should go, and when they should press the brake pedal, where they should go, how they should behave, basically. So one God agent control everything. And also you can interact. The simulator can interact with the programming languages through Python API, and I think C API as well. You can control actors' properties. You can read and write event and sensor data. You can read like genesis information. You can see if there is a collision. You can get LIDAR and radar data. And I think you can even specify you can change or specify the landmarks and maps. But yeah, I haven't tried them yet. So let's see how Åkerplatsen is modeled in this in the CARLA. Again, so if you have been in Gothenburg, you can go to Infotiv office in Västra Hamngatan. It's very close to downtown, basically. Here is Domkyrkan, and here is the Infotiv office. And if you walk across the canal, you can go to the Åkerplatsen, and there is a Clarion Hotel here. The picture, the video that I showed you was taken from this Scandic Crown building. So here is the 3D model of the basically part of the city. This model is extracted from OpenStreetMap. Basically, we haven't done much. The roads are as described in the OpenStreetMap, and some of the buildings, the description and the shape of buildings are also extracted from the OpenStreetMap. Right now, you see that buildings have no texture, and they're like a wooden blocks, but you can easily replace them with other 3D objects. And these roads, you see these shapes of roads are described with OpenDrive, are described in the OpenDrive format. So using the API, I drop 2 agents in a moment. Yeah, one car is dropped here, and I ask the car to drive in the road, basically. I'm not controlling it. It's like driving in the middle of the road and following that path randomly, basically. And there's also a motorcycle driver. There's also driving in the middle of the road toward the square, basically. And yeah, here is the Google Street view of the same location. It's very incomplete. That's what we got from OpenStreetMap without adding any extra, 3D object or improving the quality of objects in the scene. Here, I also dropped a Tesla car that I'm manually trying to drive. You notice that I'm manually controlling it because I'm a very careless driver. And also notice the road and the asphalt, and notice that it's raining. I hope that the video has a good quality enough to notice the raindrops on a road. So yeah, I'm driving. I'm a bit careless, but forgive me for that. Yeah. Notice the shadow of this building, the reflection of sun, reflection of lights on the road, and the puddles. Reflection of that building here. So we got this basically for free. We just imported the OpenStreetMap, and bam. CARLA already support camera semantic segmentation, which means that you can, the blue part is the car, the purple part is the road, for example. You can easily identify there is a LiDAR sensor, dynamic vision sensor, camera RGB distorted, and normal camera. And here, if you notice this, there is also, I think, radar sensor. Like you can see, when the speed changes, these points also change their color. And you can also notice that when you cross the cross a lane, you can receive some signal in your API that you passed over a lane. Another thing is that these are not just images. Like here, there is like you see this from the other picture as well. As we pass over this train track, notice how the physics of the vehicle changes. Maybe I should go back a little bit. Like, yeah, you see that the car shakes as you drive over the train track. Yeah, again, I think the use case that we are working is about like these traffic cameras that read license plates. And we thought that in future we will change the license plate and see how we can integrate how we can read the license plates, and we can compare it from real world to the simulated world. I think that's it for this. Oh, sorry. If you want to know more about CARLA and self-driving car, there is a course in the Coursera. There's a specialization in the Coursera about self-driving car, which contains several courses, and they are using CARLA for this purpose. And there is, as I said, most of the movement here are either in the autopilot mode or manual, like I was controlling the car, but you can also install AutoWare agent and control how, like you can actually install ML model to control the car, which is something that we are consider doing it. We haven't tried it, but it's part of our goal for now. Well, we don't know. We should see if we can gain anything out of it. Yeah, that was my presentation. Thank you.
In this training module, I will present and discuss model-implemented fault and attack injection. They are experimental verification and validation methods. They have been under development at our department for over 10 years now. So my name is Peter Folkesson, and I work as a researcher at the Dependable Transport Unit at RISE Research Institutes of Sweden. So first, a little bit about injection-based verification and validation. So these are, in contrast to the analytical techniques, experimental techniques that work by introducing artificial faults or attacks into the system. And they do that in order to evaluate dependability or security characteristics of a system. One way of classifying these techniques is to divide them into either physical techniques or simulation-based techniques. Physical techniques are techniques that inject faults and attacks into actual physical systems or prototypes, while simulation-based techniques uses simulations of systems instead. So physical techniques, in its turn, it can be divided into hardware-implemented techniques And these techniques, they use extra hardware for injecting faults and attacks, and software implemented techniques, which uses extra software instead. Some examples of hardware implemented techniques, for example, pin level fault injection, radiation-based fault injection, injections that use the debug logic of circuits, and FPGA-based fault injection, and so on. Now, numerous simulation-based techniques exist, and model-implemented fault and attack injection are examples of simulation-based techniques. Also, the simulation-based fault and attack injection at system level that was presented at the previous part of this training session belong to this category, as well as many other techniques that use simulators, like simulators at the hardware level, for example, VHDL simulators. So the tool we have developed and used for model implemented fault and attack injection is called Modify. This stands for Model Implemented Fault Injection Tool. Our tool targets systems developed as Simulink models, and it uses the MATLAB Simulink environment for injecting fault and attack models. And these models are also developed as Simulink models. So this technique is therefore useful for early dependability validation of software developed as models. A large number of fault and attack models are already included in the tool. For example, there is bit flip faults, models supporting sensor faults, and various attack models like replay attacks. More fault models can also easily be added by the user. There is also support for analyzing and visualizing fault and attack injection results with this tool. So the process for injecting faults is shown here. Faults can be injected on the output or input signals of any block in the target system model. Single or multiple faults are possible, as well as sequences of faults. The target system model is instrumented with a chosen fault and attack injection model at chosen locations. And this is done at the start of the simulation. So in this figure, you can see a bit flip fault model has been inserted into the target system model. But this bit flip fault model is only activated at a chosen simulation time point. Otherwise, it just passes the signals that goes through it. So by applying this technique, there is minimal intrusion on the target system, like simulated time or the nominal behavior of the system. But of course, there is some effect on the simulation execution time due to it, the extra Simulink models added. Now, all fault injection blocks are defined in the Simulink library. And this library currently includes bit flip fault models, which are able to emulate the effects of transient faults in, for example, a microprocessor. But there is also stacked fault models, stacked 1, 0, value, or in or outside of range. And these faults are able to emulate the effects of permanent faults in the hardware. Apart from these, there are different fault models for sensors, and these are comparable to those listed in part 5 of the ISO 26262 standard. And these are shown in this figure here. So apart from the stacked faults, these fault models include offset faults, oscillation faults, and gain faults. And as I mentioned, the library can be further extended by the user with additional fault models. And these fault models can be either generic, that is, they are can be applied to any target system, or target-specific fault models. Now, we are relying on the fault injection principle for simulating security attacks as well. This is the fault, error, and failure chain that was presented by Avicienis, Jean-Claude Laprie, Brian Randall, and others in, for example, the fundamental concepts of dependability from 2001. Here, a system failure is defined as a deviation from the intended service. A failure may occur because there is an error in the system, defined as a deviation from the correct system state. And the cause of the error is called a fault. And there are many kinds of faults. It can be shortcuts, it can be breaks, it can be software bugs, and so on. And these may all be classified according to their phenomenological cause, their intent, the affecting domain, whether they affect hardware or software, the system boundaries they occur from, and when they occur. So according to this classification, an attack may be considered a special type of fault. And this fault is human-made, it's deliberate and malicious, it affects hardware and software, it occurs from the external system boundaries during the operational phase. Now, this attack, if it's successful from the attacker's perspective, may lead to an intrusion in the system, which may be considered an error. If the intrusion is not detected by an intrusion detection mechanism, for example, then this may lead to a compromised system, equivalent to system failure or a deviation from the intended service. In Modify, we have several attack models already included, and we have chosen to map our attack models to the Microsoft Stride threat model. Here, the threat space is divided into 6 threat types. There are spoofing, which are threats related to falsification of identification or data. Tampering, which are threats related to manipulation of either data or code in the system. We have repudiation, which are threats related to actions being not traceable to the attacker. We have information disclosure threats, which are threats related to illegal access to data. We have denial of service threats, which are threats related to resource being unavailable or disabled. And finally, we have elevation of privilege threats, which are threats related to increased privilege for accessing unallowed resources in the system. Now, the tool currently includes generic, that is not system-specific attack models, corresponding to 4 of these threat types. Currently, we have corrupt data or code, and corrupt messages corresponding to tampering threats. We have replay attacks corresponding to repudiation threats. Intercept attacks corresponding to information disclosure threats. And jamming attacks corresponding to denial of service threats. So, when it comes to result analysis from the tool allows us to classify the outcome of each fault and attack injection experiment in the way shown here. So, a fault or attack may lead to either effective error or a non-effective error. Effective errors are errors which are either detected by an error detection mechanism in the system or lead to an undetected wrong output. Now, these undetected wrong outputs may be further classified according to how severely they affect the target system and its intended service. and this is typically governed by the system requirements. Non-effective errors. These are errors which do not cause any change in the observational behavior of the system. These may be classified further into either latent errors, which are errors which remain in the system without being detected or cause any undetected wrong outputs, or overwritten errors, where all the effects of a fault are overwritten. For example, if you inject a bit flip in a CPU register, and this register is written to before it's being read, then we have an example of an overwritten error. Now here, relevant metrics which are obtainable using this classification include error coverage, which using this classification may be calculated as the number of detected errors plus the number of non-effective errors divided by the total number of faults. And this, we can say, is equal to the 1 minus error non-coverage, where we can calculate the error non-coverage as the number of undetected wrong outputs divided by the total number of faults injected. So, to facilitate the analysis of fault and attack injection results, we have developed a database for storing the results, which we call FIND, which stands for Fault and Attack Injection Database. Now, this database is capable of storing results in a generic, that is, tool-independent format. So we think that apart from speeding up fault and attack injection campaigns and analysis, this database simplifies comparison of results from different fault and attack injection tools, which can then be performed at different abstraction levels. The database stores campaign configuration information, like the type of injection, locations for injections, and time points for injections. It also stores the observed behavior of the nominal system, which we call golden run, and of course the observed behavior of the injected system, the experimental runs. Now, connected to this database are various tools that helps us analyze and visualize the fault injection experiments. So these include generic classification scripts like SQL scripts, views, and store procedures, but also a tool for visualizing experimental results, which we call Find Analyzer. Here are some of the publications discussing the model implemented fault and attack injection methods that we have presented during the last decade. The method was first introduced in 2010. Immediately followed by a presentation of the first version of the modified tool. In 2018, model implemented attack injection was presented. The tool has also been used in projects together with our customers, mainly in the automotive and avionics domains. So in values, we are looking at speeding up the safety and security validation process for model implemented fault and attack injection. As part of this effort, we will look at methods which will improve the confidence of the validation results. For example, obtained using random sampling of the available fault and attack space. And we do this by reducing the required fault and attack space. In this case, we define the fault and attack space as consisting of the fault attack model used, the location of the fault and attack, and the point in time of the fault and attack. We investigate two techniques for this. First, we are looking at pre-injection analysis, where we analyze the target system before injecting the faults and attacks, so that we may focus the faults and attacks which are effective and the results are unknown. Some techniques we are looking at here include inject on read. Here we only inject on signals when they are read. Inject on write. Here we only inject on signals when they are produced. And aerospace pruning of signals. Here we identify and eliminate equivalent signal locations in the target system model. Then we are also looking at post-injection. Here we perform analysis after injection in order to either predict the results of subsequent fault and attack injections or focus the fault and attack injections based on previous results. For example, we have sensitivity profiling technique. Here we identify and focus our injections on the parts of the system which have been identified to be the most sensitive. And we have error propagation analysis, where we identify and focus on the parts where fault attacks have been found to be most likely to propagate. And then we have some other ideas which also includes the use of, for example, machine learning. So these are some limitations of the method which we believe could be addressed by pre and post-injection analysis. Regarding functionality and cost limitations, we believe that adding pre and post-injection analysis would reduce the number of tests and could still give the same results. So in this way, we will reduce time, cost, and effort of performing the experiments. For scalability and computation limitations, they will also be addressed. For example, if you perform exhaustive fault and attack injection, these may require intense computational resources, depending on the complexity of the target system and its environment. So by reducing the fault and attack space required, less computational resources will be needed. So in this project, we are going to apply our fault and attack injection method on at least the aerospace use case 5, the aircraft engine controller. But if it's possible to use the method in any of the other use cases of the project, we would be much interested in applying our technique on those as well. Apart from incorporating the proposed pre and post-injection analysis in our modify tool, we are also interested in combining model-implemented fault and attack injection method with other analytical verification and validation methods, which we believe would facilitate pre-injection analysis. So let me show you the tool. So this is the MATLAB Simulink environment. We have an example model and the fault and attack model library open here to the right. So we may launch the modified graphical user interface directly from MATLAB by entering Start Modify. And this graphical user interface allows us to configure the experiments. We may select which model we will perform experiments on and how the experiment should be conducted. And as I said, here is an example break-by-wire application that we have used in many previous research projects. As I said, the tool is able to inject faults on all input and output signals at any level of the model. And the fault and attack model library can be extended by the user. Here we see the fault models at the top that we currently have, and the attack models at the bottom. Now let's perform an attack injection experiment. We have a simple test canvas model, which will the sender will send data that it receives from the outside to a receiver. And the stimuli, the input to the sender, is given in a stimuli file that we have to provide. And then we launch and execute the model with the provided stimuli. And this way we check that the model works, and we also get the structure of the model and the golden run, the nominal behavior of the model. The next tab, we can select campaign-wide settings, like the number of experiments. Let's just use one here. And also if you want to conduct random injections or exhaustive injections. The next tab, we select which attacks or faults we want to perform on which locations and which point in time they should be injected. So we see a tree structure of the complete model. And also it picks up all the fault and attack models from the fault and attack model library here. They are automatically entered here. Let's select a replay attack on a certain signal in the model. This is a configurable replay attack, so we may enter how many steps we want to replay. Let's replay two values that are 3 time steps old. Now let's inject this replay attack at time step 4. So let's now save this campaign configuration so that we may repeat this experiment later. And let's execute the campaign. The results are stored in the find database, but also in an XML file for backwards compatibility with older versions of the tool. Now we performed one experiment and it was successfully performed. So let's open the find analyzer, which will allow us to connect to the database and look at the results. And for this purpose, we have a Find Explorer tool available. So here we see all the campaigns that have been conducted that are stored in the database, and at the bottom we see the latest campaign. Let's open that by clicking on it. And at the top, we see now the golden run, the nominal behavior of all the output signals on the model. And in the middle, we see all the experiments that were performed. In this case, just one. Now we plot the nominal behavior, and it just counts upwards from 0 to 9 for each time step. So we may also filter the experiments, look at all undetected wrong outputs or all effective errors and so on, and get the complete classification of all the experiments. And we see that we got an undetected wrong output here, silent data corruption. Let's click on the experiment, and we can see the output from this experiment. We can add that to the plot. And now we see the effects. At time step 4, we performed a replay attack, 3 time steps old, and we did it for 2 time steps. Now, in order to facilitate using the tool in tool chains and automatic workflow processes, it's possible to launch the tool in the background as a batch job as well. Let's show that. And we need to pick out out which configuration it should run. And we can use that configuration we just saved. So now it will perform the same experiment, but in the background. So it launches the tool, do the checks, stores the golden run, and then immediately performs the executes the experiments. And we can see in the database this last experiment. Let's refresh the contents and see at the bottom there we have a new experiment, new timestamp. Can plot this. Can also plot, add where the attack was injected. And we got the same area. So, thank you.
So good morning, everyone. As David has said, I am José Luis de la Vara, and I'm going to briefly introduce this method, model-based assurance and certification, because actually, well, it covers many more things than what I can present in 20-30 minutes. As I will explain, this has been developed, I would say now for almost 10 years, more than 10 years actually. So it integrates different aspects needed to assure and certify a system. And I will give you many pointers to other sources where you can find more information. This is an old slide, actually, and well, it not covers everything that I want to present, but so that everyone has a common basis on what we are dealing with, even though I assume that most of you know the context of this method. But well, anyway, as you know, we have nowadays computers and software everywhere, car engines, airplanes, oil platforms, and there is a need to ensure that these systems are safe. Well, actually, for values, we also need to ensure security and privacy. And there is an overall principle in these critical domains that any system is guilty until proven innocent. So that means that we have to make others develop confidence in the dependability of the systems. And one common way of doing this is that for different application domains, there are different standards that deal with functional safety, software assurance, hardware assurance, and it's assumed that if you follow this standard, your system will be dependable enough. So once you have followed these standards, we explain what you need to take into account when developing a system, some best practices. There will be some third party that will approve your system, certify it, or will issue some kind of conformity assessment confirmation. So in a bit more formal way, when I talk about assurance, I'm talking about the plan and systematic activities to get justified confidence. So this means that you need, for example, evidence to confirm that a system satisfies some requirements for safety, security, and so on. And typically, this is done in compliance with the standards. And when I talk about certification, it's the legal recognition. This applies to some domains, not to others, that a system is dependable and complies with the standards. As I have said, in values, we do not only deal with safety, even though this method was initially defined for safety critical systems. It can now also be applied to other dependability concerns, such as cybersecurity and privacy. And with this picture, what I want to show is the fact that when we are dealing with assurance and certification, These processes affect the whole life cycle of a system, since inception until the commission. So we are covering all the different stages, activities that affect a system. Well, as I have already mentioned, it affects different aspects of a system, safety, security, and so on. What happens with these activities in practice? This is only a few points about how these activities are in reality. They are complex and they are labor intensive. They require a lot of resources and detailed attention, rigorous attention to how to develop the systems and to collect information about the life cycle. We need to manage the compliance with the standards, the evidence to show that we are complying with the standards and that the systems can be deemed dependable. That also needs to be justified. As we are dealing with complex activities, there is a need for approaches that facilitate them and ideally that increase their efficiency. As the systems evolve and become more advanced and more complex, the same happens with assurance and certification. So we need to take care of new, for example, characteristics of the systems, such as when embedded systems now have become self-physical systems, so they have new connectivity functionality that poses some new challenges on how to assure a system, for example, regarding security. And in general, practitioners expect improvements on both the methods and the tools that support these activities. Just to give you a short overview, and in some cases you will know better than me because you are directly dealing with these activities on your industrial practice. Sometimes this is done in a very, I would say, archaic way, like using Excel spreadsheets. When that way you don't have the information integrated, it's difficult to identify inconsistency issues, for example, or even to assess completeness accurately. So how can models help in these activities? This is only 3 points that I can highlight about the kind of issues that we can, source management, we can improve with models. So at the end, in simple words, there's a problem of managing a large amount of information about the systems, the standards to comply with, how to justify dependability. And if we don't deal accurately with these needs, certification risk can arise. So by these risks, I mean that a system supplier or component supplier is not able to develop a dependable system, that the supplier is not able to demonstrate that the system can be deemed dependable, or that a third party, some assessor, certifier, doesn't develop enough confidence in system dependability. So not only but the argument of several researchers and practitioners is that if we use structure specifications in the form of models, they can be diagrams or in some textual way in addition. So by using this structure specification, these models, we can aid in activities such as compliance, evidence, and argumentation management. How? Well, once we have these specifications, they will help us to analyze the correctness of the information, the completeness, consistency, and so on. This is the general process that I will present for model-based assurance and certification. Actually, you might have a different one in mind because this is only a way to structure the activities for description purposes, and we could even refine or add some activities. But I would like to set the general scope of the method. We have divided this method in 6 activities. That is what you need to do when having to deal with certification and assurance. So first of all, you need to determine what compliance aspects you might need to take into account for your company. You can also analyze what process aspects can be reused between one project and another. This is related to variability. Once you have a concrete project, first of all, you need to define the compliance needs for that concrete project. So it's not the same developing a software and a hardware system. That will also vary according to the criticality level of a system. It's not the same A, than D. So you have to configure your project, the compliance needs of your project according to the system or element that you are dealing with. This part corresponds to the engineering side, let's call it. We're going to present aspects about the design, analysis, and the verification validation of this design according to the approach. So we are following a model-based approach. So we are focusing on model-based systems engineering activities. In this case, that they relate to the requirements, architecture, and design phases of the system life cycle. And finally, we need to justify dependability with assurance cases. And this is transversal, even though it's at the end. We need to collect the evidence. We need to collect the artifacts that will allow us to justify that the system can be dependable and that complies with the standards, applicable standards for a project. And one thing I would like to highlight here is that what I'm going to present is a holistic, integrated approach. So what do I mean by this? Well, typically, and in fact, this is something that was done in a previous project, these activities had been managed somehow in an independent way. So, for example, in this new approach, we are basically linking the assurance cases with the system architecture models to justify the suitability. They are not now independent activities, but we are integrating everything so that we can also, for example, check the consistency between the different activities and the information managed. As I have said, I cannot present many details because of the amount of time that I have at my disposal. But basically, what happens at the end is that there is a meta model, a data structure for a project behind all these activities that links how the information can be managed and how the information relates from one phase to another. I will now briefly present each activity. But before that, I would also like to highlight that when this method was developed, we had in mind many different stakeholders and users, not only, for example, engineers, but also the kind of needs that a project or assurance manager have in assurance and certification projects, or also the needs of assessors, the people checking how a system is being engineered and its compliance. So the first activity I was mentioning, standards compliance definition. So this is an activity that is not related to a single project, but a company develops and can reuse between projects. So basically, what we have to do is to represent how we can comply with a standard. So this requires that we analyze and represent the requirements from the standards, the activities to follow, the artifacts to manage, the techniques that can be used, also considering how these elements can vary depending on, for example, the criticality of a system. And this is represented with a model that we will later use, as I will explain, for a given project. And we can also deal with the mapping between standards. Why do we need this mapping? So there are different scenarios for this. Typical ones are, for example, if I want to assess how compliant I'm with a standard, considering that I'm complying with another. So if I have complied with automotive spice, I might want to know how compliant I am with ISO 26262. And also for reuse purposes between projects. For example, if the criticality level of a component changes because of the way it has been developed or used, better said. I can also exploit those mappings to see how compliant I would be in a new situation. Regarding process usability definition, so this is mostly a matter of identifying elements of possible processes for the projects, activities, roles, techniques, and how these elements can be configured according to the characteristics of a system or a project. So that is mostly represented with some kind of variability diagram or model like this, in which we have constraints about when an element applies or how they have to be combined. This is also, as I didn't mention it, a project independent activity. It's something that you do once, and once you are dealing with a given project, you would select those parts that apply to your project. Assurance project definition. This is now a project-specific activity, and this is the main idea is that, okay, once I start a project, I need to configure how that project has to be regarding assurance certification. So in simple words, for example, once you have the complete model or the whole model of a standard, in this example, DO178C, you can select the parts of the standards, activities, or artifacts that apply to your project according to its characteristics. And also at this stage, you can manage, analyze the possible reuse of information from other projects. Imagine that you are developing a new version of a system, so you don't have to do everything from scratch, but you have some certification information that you want to reuse, or that you are in a maybe not so frequent, but also actual scenario. If you have developed a system or a component for a given application domain, something for avionics, and you want to reuse it to sell it in automotive, you can exploit the use analysis possibilities of the method to see what kind of information is needed or what kind of information can be reused from a previous certification project. Now I'm entering into, I would say, the more system concrete activity, which is system design analysis and B&B. So as I have said, we are following a model-based system engineering approach. And concretely, that's because of the activities we are focusing on. We deal with requirements, architecture, also the specification of contracts for the components, and we link all these activities with the execution of safety and security analysis. Currently, this is mostly done with SysML and some extensions, for example, with chess. So I understand that probably Silvia will present some more details about how to model the systems and analyze them in the next session. So I'm not going to present too much about that. And well, if you have any question at the end, you can ask me. And I have said that I have included pointers to other sources of information. In many projects, in many domains, you also need to create structure representations that justify why a system or component is dependable, how it complies with the applicable standards, and so on. So this is done with assurance cases. We also can use this activity to analyze possible relationships between safety and security to see if the system, for example, if there are conflicts, if we can suitably fulfill both quality concerns. And we can also link the information from the system models, system architecture models, and assurance cases to justify the suitability of our design. Well, and there are some other advanced mechanisms, which I'm not going to explain because if you are not very familiar with this technique, they will sound strange to you. But anyway, you can, for example, structure the resonance cases in modules for reuse purposes. You can create patterns to instantiate them. And the last activity, even though actually it's, I would say, a transversal activity, is to collect the information of all those artifacts that correspond to evidence for your project, evidence of compliance or evidence of dependability. So you have to characterize the artifacts, specify their life cycle, manage their traceability, and also considering process execution aspects. So at the end, we need to keep track of the life cycles of the artifacts, and we will later use this information to specify how we are complying with a standard or link them to the argumentation to justify the dependability of the system. The current version of the method is mostly the result of the AMAS project. Many of you know the project because you were also involved. So we were dealing with a certification of several physical systems. And one of the main resources that we provided was the integration and actually also further development of results from previous projects, OpenCOS, Safe Searches, Crystal. So this is also what I meant by the holistic integrated approach. We had results from different projects. For example, OpenCOS focused on compliance management, and CHESS focused on system model analysis. So we have managed to integrate the results from both projects to provide a broader and integrated approach. In AMAS, the approach or the method was used in 11 case studies, but actually the number of applications is higher if we consider that in each of one of these projects there were further case studies. But well, in simple words, the integrated application has been done in 11 case studies, and we have also case studies in which individual elements of the approach, of the method, have been used. I'm going to highlight some further characteristics of the method. One thing that, in my opinion, is very important is that, in my opinion, there is quite good documentation about the method. I'm talking of hundreds of pages. Also, the most deliverables of AMAS are public to see how the method was developed. So this also contributes to helping data user applies the method. There exists an integrated platform, which is called the OpenCert, sometimes referred to as a AMAS tool platform, that supports the application of the method. I don't have time to go into details, but as I will say now, you can find a lot of information in other sources. Something also very important, the OpenCert or the AMAS tool platform is integrated with external tools. So this satisfies different needs. One is that someone can provide some kind of added value feature. For example, Moreto, this is a tool by AIT that focuses on security analysis and with which you can exchange information in the AMAS platform. And in other cases, you also need to collect evidence information, evidence data from external tools for your project. For example, the RQA tool by TRC analyzes the quality of system artifacts, and you can import that information to justify that you are compliant with a given standard, for instance. Another important result from AMAS was the creation of an open source community. This is part of Eclipse. So in what is the most relevant to us, what we can contribute to the community. In fact, there are some values partners which are already official members of the community. That also means that we can download the application, we can download the code, and we can tailor it as we need. And well, I didn't mention this detail yet, but this is shown here. At the end, this AMAS tool platform integrates different solutions, different open source solutions, Eclipse projects, that cover different needs of the method. So that was, for example, Chess for system modeling, EPF for process engineering, Papyrus also for system modeling. So there are specific links with these other projects. And this is something very important, in my opinion, for you, in case you're interested in the method. There exists this YouTube channel, which we created in AMAS, and we have over 50 demo videos, including also training videos, videos focused on some concrete use case. Sometimes I would even say that the amount of information is overwhelming to be able to really have a good picture, because we are covering so many things that well, at the end we really can provide much information about many different aspects and needs for us and certification. And I mean, now in the last part of the presentation, so what kind of strengths I can highlight? So in my opinion, one very important strength is the extensive validation of the method. It has been applied in many different use cases for different application domains, different projects, different scenarios. So that makes us confident in the suitability of the method. It's already part of an Eclipse project, which has some advantages, as I have mentioned, about the reuse or modification of the tool support. It's integrated with other methodologies and tools. This is also a very important need in practice. And well, this is mostly a tool-based aspect, but there exist integration extension mechanisms. So if we want to integrate another tool, there are some features in the tool support that facilitates them. And as I also said, the amount of guidance, and in this case, methodological guidance for a user, which is a very good and important point, in my opinion. Limitation. Well, the first point is not a limitation, but you can also see it as a need. But at the end, since we are providing a generic method, you always need to tailor it to a project. Almost often need to tailor it. This also implies that you have to select the activities of the method that you need for a project or not. So, for example, maybe in one project, you don't need to create assurance cases in a structured way, so you can skip that activity. If we think of tooling aspects, maybe you are already using your own tool for system modeling, such as Enterprise Architect, so you don't need to use tool support for that, but you can have to integrate it somehow. There is a subsequent limitation on this, is that the current tool support doesn't support very well workflow configuration. So if you have this need that I am mentioning about not taking care of one activity, integrating OpenShift with other external tools, let's say you have to manage that manually, whereas there could be some kind of a wizard, some further more advanced support that could guide the user on how to configure a workflow according to a given tool chain. And the last point, well, this is actually not a limitation of only OpenShift, but also a limitation sometimes of how Eclipse applications are developed and how they are. So sometimes you can improve their usability. In our case, we use a lot of technologies for automatic code generation, so that has some advantages, such as fast development, but sometimes in this case, the features of the kind of usability characteristics of the final application can be improved. This is actually one of the main aspects to improve according to the practitioners that have used OpenShift in their use cases. For values, we are currently focused on use case 3 and 8. 3 from NXP, a radar system, and 8 from RGB, a neuromuscular transmission system. We are in principle mostly dealing with compliance management, and we are also open to apply the method in other use cases. So what kind of things we need to address? For RGB, for example, the method hasn't been applied yet to the healthcare domain. And this also imposes, for example, the need of tailoring the method to their engineering process. Also paying more attention to product-based standards. So far, the method has been extensively used on process-based or goal-based standards, but not so much on product-based standards, which indicate concrete features for a system, not so much the process to follow to develop it. We're also interested on continue working on cross-standard compliance analysis. There are some possibilities that we can incorporate in the method, for example, to improve gap analysis. And we also refer to this. There will be for sure a need of integration with other activities according to the needs and situation and scenarios of the use cases. So to conclude, well, I think I'm more or less on time. So I hope that if you didn't know it, you have seen that attachment and certification are complex activities. I haven't been able to explain all the details, but at the end, what we claim is that with this model-based method, we can support the activities and even improve them. The current method is a result of the AMAS project, which integrated different existing tools and methods into a single approach for compliance management, system analysis, and so on. The method has already been applied in a large number of use cases. We have tool support available, good guidance. So I think all these elements are important for the validity, also to facilitate the usage of the method. And well, in general, in values, we are going to extend the application, the scenarios in which the method has been used, and this will also require that we will have to adjust, include some new elements, define new guidance on how to use the method in an effective way. So that's all from my side. Now, if you have any questions, comments, this is your time. As I said, I haven't been able to provide all the details, so because we don't have so much time. So in any case, if you need more information, you can contact me later. You can access the sources I have referred to in the presentation. There is many more things behind the method than what I have been able to explain in half an hour.
My name is Silvia Mazzini. I'm from Intex. I will present this methodology that is model-based safety analysis with the failure logic analysis. That is one of the analysis that is described in the deliverable 3.1 under the name model-based safety analysis. This to clarify, there is another methodologies that is proposed by Fondazione Bruno Kessler. This is only the part proposed by Intex, and this is a techniques for model-based safety analysis that is applied. We will see how it is better. Okay. So generally, I have a short introduction on the principles, and then I will present deeply the methodology. Model-based, first of all, what is model-based safety analysis? Is an analysis approach in which the safety expert, can rely on models for safety analysis and use automated analysis tools to analyze the model behavior. Therefore, this methodology implies a shift from a safety analysis that is performed on documentation to a safety analysis that is based on models and is automated as much as possible. Just a short reminder, safety is concerned with failures that may lead to hazard, and hazards are potential unsafe conditions resulting from failures, malfunction, external events, error, or any combination. And the principle is that safety analysis shall proceed in parallel with the system design, with interaction between the two activities to keep them updated during the work life cycle of the system. This is the principle we want to address. And classical safety analysis are based on failure mode effect analysis, FMEA, shortly called FMEA, and fault tree analysis, that are two classical safety analysis considered that we consider in our approach. FMEA is based on inductive reasoning, while FTR is a deductive analysis. So FMEA consider the failure or part of the system and analyze the impact on the product failure. While for tree, we start from product failure and we analyze what are the combination of components that led to the fault. FMEA in particular helps identifying potential failures, causes, and impacts. And helps in identifying the action to reduce and eliminate these potential failure modes. In particular, helps to define countermeasures and safety requirements. FMEA involves reviewing many components as possible to identify failure modes, cases, and effects. And for each component, the failure modes and causes and results effects on the system are considered. So here I have a generic worksheet for FMEA as derived from the IC standard 60812. And this is a template, a generic template, but there are many variants that with a few additions for different application. But this is a techniques that is applied in many domains. For complex systems, the application is to identify, FMEA helps to identify critical items and requirements for design improvement and correction. Typical order, we start with the functions that constitute the system and consider them as main components of the top system block. And this is done essentially at concept level to timely detect possible failures leading to system malfunctions. While the system lifecycle progresses and we have lower level information on major system blocks, we can progress lowerly to lower level as necessary. And what is and the application is that FMEA is applied and refined to upper levels and back, traced back to the system level in order to keep it updated during the life cycle in an iterative manner. For tree is a top-down deductive system failure analysis. Given a system undesired event, it specifies a method for identification and analysis of the possible causes. So we consider a top event that is an undesired event, and the associated lower level basic events that can lead to such top event. And basic events are combined in a Boolean logic. Just to explain the essential points of fault tree. Fault tree is first qualitative, then can be used also in a quantitative way by association of occurrence probability to the lower level event. Typical points of analysis for fault tree are common cause events. So the analysis of the different events, so the establishment of the common cause events that are the different events in a system that can have the same cause for their occurrence. That may bypass redundancy, for example. Common mode failure, event that affect a number of elements that can be considered independent. Minimal cut set is the minimal set of primary events that cause a top event. And single point of failure, sorry, is a very critical event that will be an overall system failure by itself. So a minimal cut set constituted by single failure event. So in the traditional safety analysis, the safety analysis is performed manually by safety expert, and relevant effort is spent in gathering information about the system architecture from documents and behavior. And the safety analysis is based on an informal model of the system and documentation, in particular from requirement documentation. Therefore, the analysis is highly subjective, dependent on the skill of the analyst, and there is no full guarantee that is complete, consistent among different analyses and error-free. And therefore, we present this model-based safety analysis with the use of techniques that is called the failure logic analysis, FLA. And we have based the definition of this methodology also on the experience, on industrial experience. So from the aim of the technologies is moved from traditional safety analysis performed manually by the safety expert to a methodology to perform a model-based safety analysis on complex systems based on the realization of system models through the use of SysML, applying failure logic analysis, the failure logic analysis techniques for calculus of the failure behavior of the system from the failure behavior of individual functions components. And it aims at the support for the safety assessment person by generation of FMEA and FTA. What are the key points is the exhaustiveness of the analysis that is supported by automated calculus, the reduction of manual effort and error possibilities in the safety analysis process, and also improve correctness, consistency between different safety analysis at different levels, for instance, in the software lifecycle, modularity and scalability and reuse of the analysis. So this methodology is supported by the CHESS toolset. In particular, CHESS support SysML modeling. There is a plugin that has been already developed in past projects for past projects like the chess, the concerto projects, and also it was slightly modified in the AMAS process that was mentioned by José Luis. And and this module has been developed by Malerdalen University in collaboration with Intex. And there are also some extensions to support fault-free, but we work on particular on extensions for FMEA generation and FTA improvement. What is the process we envisage in this methodology? The methodology applies in different domains, and we expect that we receive a functional system or physical architecture from system engineers in the project, and the core of the methodology is that there is a system model, so there is a functional and physical architecture model is developed through the use of SysML. And then the FLA failure logic analysis is applied in the extended architecture with the help of the safety expert. In particular, failures and propagation rules are defined by addition in the architecture, and then we are able to extract FMEA tables and complete them, and then generate fault trees. And in this project, the safety experts will be able to expose safety requirements and failure events can be useful output for success failure for VMV applied or fault injection applied based on the failure that's been envisaged. The methodologies is based on the definition of a functional architecture view. The functional architecture view shall contain the function, the definition of the system function and their breakdown into sub-functions. Therefore, the process is to identify all the system function and break down each system function into more specific ones. And express the relationships among some functions. So this is an example. We have a system function architecture with SysML using a block definition diagram in which all the system functions are defined and their breakdown in sub-functions. Then the system function architecture is described with the internal block diagram in which we can look at how each subcomponents is interrelated to implement so how the sub-functions are interrelated for a specific function, how internal functions are related. And we see the connection between input-output ports of the external functions are related to the input-output ports of internal sub-functions. The physical architecture then can be defined in a similar way, considering how the system implements the functions, and relying on the decomposition of the system with focus on the physical subsystems, for instance, equipments and components that make the overall systems. And we apply the allocation possibility to relate the functional architecture with to the physical architecture. So the functions that have been developed in the functional architecture are related by allocation to the elements of the physical architecture. So we use the system, the SysML allocate relation to trace subfunctions to physical components. This is an example of physical architecture in which we have the allocation of functionalities from, we can see in the description of the allocations. Let's go to the failure logic analysis. Failure logic analysis is a technique for the calculus of the failure behavior of the system from the failure behavior of individual functions or components. It is based on a technique that is failure propagation transformation calculus, that is FPTC, that is described in the literature. Sorry, this is I've not mentioned it in the slide. And the references are in deliverable 3.1. The analysis considers the function decomposition down to basic sub-functions, and each lower level subfunctions is analyzed to identify the potential failure modes systematically, and for each failure, their propagation rules are defined. What are the failure types that are considered in these techniques? Failure are abstracted in these techniques because it is considered to be provided at the very high level, starting from the very high level of the system. The failures are divided in three types: timing failures, for instance, early on late deployment; value failures, that means out of range values; or provisioning failures, for instance, that are loss of function or uninterpreted delivery of function. So in particular, we can see a table with the kind of failures. We have early failure. The output is provided too early or late. The output is provided too late. Coarse means that an output deviates from the expected range of values. Subtle, consider the output deviates from expected range in a way that is undetectable. Omission, no output is provided, and commission, an output is provided when not expected. What are the rules for failure propagation? So the propagation is the way a failure may be transformed from into another. So failure might transform or mutate into another failure due to internal or external stimuli in a component. And therefore, the failure behavior of a component may propagate in the sense that the failure is received in input as is, transform it into another failure, so changing the nature of failure from one type to another, behave as a source of failure, generating a failure despite the absence of failure in input, or behave as a sink, that is avoiding the failure to be propagated or transformed. This is the syntax of rule definition. Each rule is composed of two parts. The left hand part specifies the behavior of the received input, and the right side specifies the behavior of an output. So each rule is of the type of length outside part into arrow a rule for the right hand side part. So an expression for the right side part. So we can have, this is the syntax, for instance, we have the ID of a port, the ID of an input, dot the kind of behavior in the right and in the left, where the behavior can be no failure or the list of failure that we have already presented. So the algorithm consider the failure behavior for each individual components and the combination of faults at the input and the propagation transformation rules, and build the set of graphs, paths, of the interconnected components in the architecture from a set of input faults to the related system failure. So from the primary events to the top event, and also consider the analysis, support the analysis in case of cycles. This approach enable the analysis of FLA paths, allows us to build the row of the FMEA table and starting from the top event to build the fault trees. For example, we can automatically generate the main field for a FMEA table, that is the function, for instance, the function, the failure mode of function, the local effect of the function, and the level on other the effect on other levels, and the end, so the effect on the at the system level. And then the safety aspect can fill in other evaluate what is the compensation, the severity, and the failure rate in order to quantify the effect. For fault tree, we have fault trees, but our analysis has evaluated that the fault tree generation is not industrial level for the moment and requires further improvements. The applicability, we will work for the applicability of this methodology in the AgriBot, and this is the methodology is fully applicable according to the ISO 26262 for the HARA analysis in particular, and also to express safety goals and safety requirements, and then can be iterated at the further levels. And also we plan to apply this methodology also for healthcare, and again the applicable standard is ISO 14971, and again there is our analysis in which the methodology can be applied. Main limitation, this is the main limitation that's been reported for the moment in deliverable 3 tree. And so there are some, according to our evaluation, there are some functional limitations, but essentially we want to consider the application of this methodology with other MS methods, model-based safety analysis methods, or connect it with the VMV methodology, for instance, for optimization of failure injection tests, and also application to cybersecurity may be explored in real scenarios. And respecting the other scalability and computational limitation, the failure propagation, the FLA algorithm can be improved for large systems, and because can be optimized for large systems. Sorry. And also the FMEA and fault tree generation shall be improved. I don't know if this is all for my presentations. I can provide some detail on the tools, but I don't know if I have more time. I suppose it has
there is
expired.
more or less 5 minutes. If you want to present something within these 5 minutes, I think we are okay with that, but it's your option.
Okay, just a short part on the toolset support. The methodology is available with the chess toolset. That is a large tool, model-based for model-based cross-domain engineering. It is based on Papyrus. Is a modeling supports a modeling language that is specialized to capture functional and non-functional properties, real-time safety, security, failure behavior, but it is based on separation of concern principles because it supports several design views, functional and non-functional views. It is specialized for contract-based design. This work has been done in collaboration with Fondazione Bruno Kessler, or main tool to main support tool are provided by Fondazione Bruno Kessler. There is a principle for component-based development that are applied in particular for software development and real-time analysis. And there are also several other analyses. This tool is available on Eclipse. Recently, we have released the version 1.00 that is a full release. The modeling language of chess is a profile of SysML, UML, and Marte that import a subset of these standard languages, avoiding redundancy and fixing some semantic variation points. But in addition, it has a large extensions profile, including the profiles are generally addressing dependability properties, and that includes also FLA extensions. And another major extension is contract-based modeling, support for contract-based modeling. The FLA is fully supported in the chess toolset through the modeling of SysML diagrams, but also there are a FLA plugin with in which that support the expression of FLA rules with the context-sensitive header based on the grammar and the analysis. There is a part dedicated to an extension dedicated to FMEA and fault tree generation. Okay, that's all. So this is how it is implemented. Is not really interesting. So I can close my presentation and ask for a question. Are any questions?
So my name is Marie. I'm from Maynooth University in Ireland, and this is joint work with Matt Luckock and Rosemary Monaghan. So I'm going to just briefly touch on a few different topics today, but I'll focus on formalizing requirements in such a way that they're actually verifiable, because I know we're all dealing with quite a few requirements. So I suppose I should introduce what I mean by verification, because sometimes the word can have many meanings. What I mean is that we're trying to determine whether or not a system meets its requirements. And of course, there are many approaches, as we've seen throughout the values project. There are formal approaches and less formal approaches, but these include things like testing, simulation-based testing, formal methods, runtime verification. There are many others. For example, even field tests would amount to some kind of verification for a system. I suppose the main take-home message about software verification is that it is necessary for certification in critical domains and to demonstrate that standards are met. For example, some particular standards may even recommend the use of a particular verification technique like formal methods for particularly critical systems. So what do I mean when I use the word formal verification? Well, formal verification isn't just checking, it's proving or disproving the correctness of a system with respect to a certain formal specification or property. And that's why it's important to formalize the requirements, which I'll move to in a little while. But I'll stick on this for a second. So just wanted to say that there are two broad categories of formal method. You know, again, there are others, but basically, these things consist of model checkers, which exhaustively examine the state space. And there was a really good talk last time about model checking, so I won't repeat too much of that. The other category of formal method is a theorem prover. So a theorem prover usually provides a deductive proof of correctness for the system that the formal specification or property is preserved. And these techniques are particularly useful, as I mentioned, when a high degree of reliability is sought for the system, or to provide robust evidence for use by regulators, again, to demonstrate that the system obeys a particular standard. So I'll just recap model checking without repeating too much about what was said the last time, because it was a really great talk. Model checking exhaustively explores the state space of a model to check whether a logical property is preserved. So when I say the space of a model, usually you have, you know, a model of the system that is written maybe as a state machine or something like that. Then against that state machine or model, properties are written in some sort of a logic, and for model checking, it's normally a kind of a temporal logic. And then the model checker checks automatically whether or not the property is preserved for every part of the state space in the model that was constructed. And if the property is violated, then the model checker will typically produce some counterexample to say why it couldn't show it for every single trace. The main, I suppose, limitation of model checking, although it's very useful, is that it does suffer from the state space explosion problem. So as the model gets larger, then it becomes more difficult to check every state. It takes up more computational power, and it is a limitation, although this is a very useful method. Again, more information. There was a great talk the last time, so I've linked that here. So theorem proving is a little bit different. So in theorem proving, you provide a deductive proof of correctness. Again, that a model, so you construct some model of your system, obeys a particular property. As I said, properties are usually written in a logic. You know, there are many logics, but for example, you can consider a property in first order logic. Theorem provers are automatic and sometimes interactive, which requires user input to discharge the proof. Interactive proofs, although they're very useful because the user can drive the prover, they can be very time consuming. And you know, theorem proving is often quite a long process, or it can be. However, it does not suffer from the state space explosion problem that the model checkers suffer from. So yeah, just a brief overview of the two main verification techniques. So they're formal methods, and formal methods can be applied at different points in the development cycle, including but not limited to requirements formalization, specification and design, source code analysis, runtime verification, to name basic but a few. There are many other different points in the development cycle. The message here is that they can be applied throughout. Of course, as I mentioned earlier, and as a few people have alluded to, verification is or can be a costly and time-consuming process, and that's whether you're using formal methods or not. However, you can mediate this by using good design practices, and I've just suggested a few things that are useful there. So things like detailed requirement formalization and elicitation can help to identify holes in the requirements at the beginning of the project. Of course, designing a system to be modular is I suppose best practice, but it makes the verification task easier because you can isolate specific components of the system. Of course, you should always isolate critical components so that you don't have to wade through, for example, a learning component to find the bit that's making a decision. And in my experience on different projects, usually a heterogeneous or corroborative approach to verification using multiple techniques, and multiple techniques I mean both formal methods, different kinds of formal methods, but both formal methods as well as less formal approaches like testing or simulation-based testing really are the best way to ensure that you have verified to a high degree. And this sort of heterogeneous approach allows you to simplify the verification burden by verifying specific parts of the system in tools or techniques that are most suitable. The only issue is that you have to also ensure the consistency between the models, and that can be difficult, but I will touch on that again briefly at the end of, well, near the end of the talk. So I'll begin by getting onto values. So in values, we're working on use case 5 with the industrial partner. So I'm going to just, I suppose, summarize some of our work on this project so far. So what is use case 5? Well, use case 5 is this wonderful aircraft engine controller. It's called a FADEC, which is something I only learned about in January, so forgive me if I'm saying it wrong. It stands for Full Authority Digital Engine Control, and the objective of this engine controller is to monitor and control the engine, such things, components such as fuel flow. In fact, I think its main objective is to optimize fuel flow. Of course, there are other things it does too. It responds to pilot input, and there's quite a lot of sensors involved that it gets input from. So when we were tasked with verifying this system, we asked for requirements. We were given some requirements from our industrial partner. And so here is just a sample of one requirement that we have been given for this use case. It says that under sensor faults, while tracking pilot commands, control objectives shall be satisfied. And then it gives an example of some of these control objectives are. And basically that specific variables are within specific limits. Now, although this requirement is useful, it tells us something about the system. It is not very easy to verify in the form that it currently is in. Because, for example, it doesn't describe what it means for a sensor fault to occur. Of course, an engineer will know what that means. But when it comes to verifying the system, we need to write these properties down in a way that's traceable, and that we can, rather than letting someone use their intuition when they're given this requirement, that it can be properly documented. It also doesn't tell us things like what are the values for settling time or the overshoot. And it's not even clear if those within the brackets, if that is a complete list of the controlled objectives. And of course, coming from, I suppose, I hadn't much experience with this sort of a system before this project. It's not even clear what tracking pilot commands means in this context. Now, of course, as I say, the person developing this will know what these things mean, but these things should be made explicit in the requirements so they're traceable from the beginning until the end. So, yes. So what were we going to do about it? Well, we started using FRET. It's a formal requirements elicitation tool. It's developed at NASA Ames in California, and it supports the formalization, understanding, and analysis of requirements. It provides a user-friendly interface, which I'll show in a second, with diagrammatic explanations of the semantics for requirements. Users use a restricted subset of natural language that they call Fretish, and it embodies a temporal logic semantics. Again, I'll show examples of that in a second. But the key thing here with FRET requirements, they fit this template shown on the slide. So they might have a scope, which allows you to write down that the requirement is only relevant for particular scopes of system behavior. Then you can specify conditions, which are, the point after which the requirement must hold. You then assign this to a component, so you can say which component has to obey this requirement. Then use the shall keyword to say that this shall happen, and you can specify timing to define the point at which the response should occur, and the response is usually that some property is satisfied. So FRET is open source and available online. So what does it look like, I guess? So here's a screenshot of the adding a requirement interface in FRET. So you can see over here, I'm not sure if you can see my mouse. So here we give every requirement a requirement ID. It can have a parent requirement, and I'll talk about that again in a minute. It is assigned to a project. In this case, we've assigned it to the project called Engine Controller. And we've written what you can add, which is really useful. You can add these rationale and comments. So you can add the natural language text for the requirement, and you can even add comments about this to help you understand it when you go back. So then we formalize this requirement, and it looks a bit like this. So if sensor faults and tracking pilot commands are true, then the controller shall satisfy control objectives. So you can see it's still quite vague, and I'll discuss that again in a second. But just to mention before I move on, that FRET also provides this diagrammatic semantics. So it gives us this diagram, and it also provides the user with, I didn't actually expand this here, but it provides the user with the meaning of each of the constructs in the diagram. So the TC stands for the triggering condition. So in this case, the triggering condition is that sensor faults and tracking pilot commands is true. And when that is true, then the response is control objectives, so it should hold. Basically, at the beginning of time, anything can happen, then this triggering condition is true, and at that point, the requirement must hold, and that's what the orange is for. Okay, so moving to the next. So again, looking at this a little bit closer, we can see that the requirement in FRET, or in FRETish, is, well, it's more concise, first of all, than the natural language requirement. But the act of formalizing it in FRET allowed us to, although we kind of knew there were some things that weren't well defined beforehand, it explicitly identifies which bits that need more detail. So for example, we've used Booleans here for sensor faults, tracking pilot commands, and control objectives. So it's obvious to someone reading this requirement in FRETish that those things haven't yet been expanded, and that obviously they should be for more detailed requirements, depending on, of course, the level of detail you want to go into. So if we expand this a little bit, so basically what happened after that was we got a hold of some sample test cases from our industry partner, and they're just, I copied them into the rationale section here, so that the sensor value deviates at most plus or minus or from the nominal value, and or the sensor value is not available, which is what it means for there to be sensor faults. So in order to decompose this, the original requirement, we considered these test cases, and that, as you can see, allowed us to make the requirement far more detailed than it was here. And this FRET gives us this parent-child relationship between requirements, which allows us to group things that are related to one another together, so that you get this sort of, I suppose, traceability again between the parent and child requirements. Now I did mention this briefly, but I didn't show an example earlier. So formalizations down here, FRET has a LTL semantic, so it produces future time and past time LTL. And if you click on those, this is what it gives you. So although they don't look very nice here, and I'm not going to go and explain what every single symbol means in them, the LTL is useful for translating to different tools. So if you wanted to use a model checker, for example, FRET can export these LTL semantics depending on which kind you want. So yeah, as I mentioned, I've showed, okay, I decomposed one requirement. We did far more than that. But anyway, beforehand, sorry, I'm ahead of myself now. So the sensor value, yes, we added in more detail to this requirement, and we do have a lot more information than we had previously. So you can see it's more verifiable, I guess, because we know exactly what we need to look for. Although we still have some unknowns, so you could refine this requirement further. We still don't know what the value is for settling time min, for example, or we don't know what OR is. But these can be added later. So yeah, as I said, a requirement can have many children, and we have constructed quite a few others from the original requirement. For example, here we have one that considers the overshoot control objectives being met. So it's similar. I think in total we have about 19 requirements currently, but we are working on making them more detailed, more concrete, so that they're more useful for the formal tools that we want to use. So you know, it's great. We have some FRET, we have some LTL, but FRET does also support a connection with other tools. In fact, you can connect a Simulink model to FRET. So you have to parse it first into a language that FRET understands, and then FRET will generate CocoSim contracts that are used to model check with Kind2. And in this way, the way that this works is you import your Simulink model into FRET, and you map the parts of the requirements which have been pulled out. So for things like the variables, the values, and the components of those of the requirements, you can map those to their counterpart in the Simulink model, and for these contracts to be generated. So you can see here we didn't add it in, but you can add in which part of the model you import the component, and you add in the type, the data type. So it provides this automatic translation into CocoSim contracts that we verify against the model using the Kind2 model checker. So of course, LTL semantics, as I mentioned earlier, can also be used to generate, well, it can be used with other tools, but to generate runtime monitors for the implemented system. And we actually did that in a prior project. We used the FRET requirements to generate runtime monitors for a robotic arm, and the runtime monitors were incorporated into the robot operating system implementation in Python for the system. So it was full traceability kind of from requirements to implementation monitors. You can also use the FRET requirements without the timing constraints. And if you notice in the previous requirements, we didn't actually use the timing constraints that are available in FRET. And in the requirements that we got from our industrial partner, most of them didn't require any sort of timing constraints. And that makes it easy to specify the requirements in other formalisms. For example, if you wanted to use a theorem prover or another specification language like Event B, it uses first order logic, the requirements without timing constraints can be very easily translated into them. Okay, so next I just want to briefly discuss some of the work that I was involved in prior to the values project. And I must emphasize that the aim of these slides is to demonstrate how the sort of requirements formalization that we have done fits into a larger system verification methodology. And yeah, so if you consider a methodology, this is a sample that we published at NASA format this year. So trying to design your system for formal verification, you can consider these steps. These are by no means a complete list of steps, but you begin by characterizing the initial system, which could be simply writing down what it's supposed to do, or just talking about what the objectives of the system are. You would develop an initial system model, perhaps in something like Simulink. Then you may perform some hazard analysis, like what Sylvia mentioned earlier with the FMEA hazard analysis. After the hazard analysis is completed, usually you will find some problems, and you will define mitigations against those hazards. And from those, you will develop safety requirements. Once those mitigations and safety requirements have been identified, usually what happens is you go back, refine the system model according to the mitigations, And then you kind of loop back to step 2 and you perform more hazard analysis until you reach a point where you've got an acceptable level of risk in the system. So at that stage, once you have these safety requirements, all your mitigations are in place. Your safety requirements are, I say, formalize is the wrong word, because at this stage they will be natural language requirements. So once you have those safety requirements, then what you can do is formalize your requirements using something like FRET and create formal models of the system. And then, of course, the formal specifications for the requirements. So after that, then you might perform verification and simulation potentially at system and component levels to ensure that you've covered everything. And then you would document your results if you needed to build a safety case, for example. And for this particular work, we were using a case study of an autonomous rover. But this methodology, as you see, is quite broad, and we think that it could be useful to explore this further during values. And it does incorporate, as I said, it does incorporate some of the approaches touched on today already, as well as at the previous training session. So again, I'll mention this is from prior work, but this follows the methodology on the previous slide. And we instantiated that methodology with specific tools. In the top half, you can see the tools are in red. So the advocate tool in the top half is for assurance case development. We don't intend to do any assurance case development as part of our work at Maynooth, or currently don't intend to do any assurance case development as part of our work at Maynooth on values. However, for that prior project, we did. So we followed through the steps. We characterized the system. We did some hazard analysis. We figured out what the mitigations and requirements were. We updated the system model, and then we made models in numerous different modeling formalisms. We had a Simulink model, a Lustre model, and an Event B model of the system. But the main part that's relevant for the values project is this sort of, we then formalize the requirements in FRET, and we use those verification tools to verify them. So I'll just now zoom in on the bits that are most relevant for values, because I didn't want to start off with part of a picture. It didn't make sense. So basically, we've currently started to formalize the requirements in FRET. As I said, we currently have about 20 so far. But of course, we are continuing to refine them and continuing to add more detail. Once we have formalized these requirements, we intend to translate them into CocoSim and Lustre. So Lustre is an intermediate language for CocoSim, which uses the Kind2 model checker. And that'll be based on the Simulink model that has been input by our industry partner. And later on, I've left the Event B stuff in here as well, because everything has limitations, and CocoSim may not be able to, of course we have to investigate this, but it may not be able to adequately specify or verify all of the properties for the project, so we may also need another tool. And I've just included Event B here as an example, so then we would also have Event B requirements, and we could do proof with Atelier B for that. And I did mention this sort of system level and component level analysis as well. So we would use a tool so CocoSim is interesting because it allows you to do compositional verification. So if we can verify all of the components and that they match their individual requirements, then it allows us to derive the system level properties and verify them from the component level properties. So yeah, I think that's all I wanted to say for that bit. To conclude then, basically, I suppose the take-home messages from this talk are that formalized requirements are useful for verification and traceability between the verification artifacts. Our use of FRET so far in this project revealed ambiguities in the natural language requirements that we can make more explicit later, and we can talk to our industry partners about that. So FRET can act as a useful bridge for communication between the academic and industry partners, and that's something that we completely agree with. Although we all talk about verification and validation and requirements, it's often the case that people have different mental models of what these things actually are. So by using a tool like FRET, it makes these differences more explicit, and it does help with communicating between different people from different backgrounds. And of course, formal requirements can simplify formal verification tasks because they look more like a logical property than a natural language requirement does, and they can help streamline the development process in that sense. Okay, so that's all for me. But before I take questions, I would just like to advertise that as myself and Matt Luckett are running the third workshop on formal methods for autonomous systems. I believe this call for papers was already sent out to the values mailing list, but just in case you haven't heard of it. We're hoping it will be hybrid with some in-person attendance in Maynooth, although it will be online in all cases anyway. So yeah, the deadlines are the 30th of July. So yeah, please get your papers ready. Other than that, I'm happy to take questions on the requirements as well. Thanks.
We have now finished VALU's first training session. We sincerely hope that you have enjoyed it and that it was a fruitful set of presentations on important topics for verification and validation of automated systems. Thank you for watching.